Oops, something went wrong. Stay till the end for a mind-blowing demo. Newton's second law of motion. Where forces meets the mass and acceleration. Don't forget to like, comment and subscribe. Let's jump onto Newton's second law of motion. In Newton's second law of motion, three components are connected to each other: net force, mass, and acceleration. Where force is the push or pull on an object measured in newtons. Mass is the weight of an object in kilogram. And finally, the acceleration, which is the change in speed of an object, measured in meters per second square. Net force is total forces in one direction, minus the total forces in opposite direction. Let's take the gist of net force. When net forces are zero. In a tug of war, when equal force is applied at both ends. Or, when a box is pushed with equal opposite forces. The net force is zero, or you can say the forces are balanced. When forces are balanced, either there is no movement or object moves with constant speed. Now, consider when net force is not zero. In a tug of war or when a box is pushed with unequal opposite forces. In both the cases, forces are unbalanced, which makes the object speed up, slows down, or change its direction. So, Newton's second law states that the acceleration of an object depends on the net force acting on it and the object's mass. So, let's get started by looking into different pushing activities. In first scenario, Ron is pushing a heavy car very slowly, but he is pushing a shopping cart easily with more speed. In second scenario, he is pushing a heavy ball on a slightly inclined plane with great effort. On the other hand, he is pushing the smaller mass ball on a similar inclined plane with more ease and with more speed. As you have seen in both the scenarios, that Ron puts greater force in pushing car or a heavier ball on an inclined plane, as compared to pushing a shopping cart or a ball of lower mass. Here comes the Newton's second of motion, which says force is equal to mass times the acceleration, where m is the mass of an object on which the force is applied, and a is the acceleration of an object caused by that applied force. Let's see what happens when we apply more force on same objects. In the first case, Ron kicks 1 kilogram of football with 100 Newton force. As we know force, F equals mass times the acceleration. By substituting the values of force 100 Newton and mass 1 kilogram into the equation, we found out that the ball will accelerate at 100 meters per second square. In second case, Ron kicks same 1 kilogram of football with higher force of 150 Newton. So, again by substituting the value of force equal to 150 Newton and mass 1 kilogram into the equation, we found out that the ball accelerates at 150 meters per second square. This acceleration is higher than when the Ron kicks with lesser force. So, we conclude that, more the force applied, more is the acceleration of the same object. When different mass objects are pushed with same acceleration, for example, 1.5 meters per second square. In case 1, Ron pushed 20 kilogram box with 1.5 meters per second square acceleration. As force equals mass times acceleration, substituting the values in the equation, we found out that 30 Newton force is required to maintain the acceleration. In case 2, Ron pushed heavier 30-kilogram box with 1.5 meter per second square acceleration. As force equals mass times acceleration. Substituting the values in the equation, we found out that 45 Newton force is required to maintain the same acceleration. This force is higher than the force required to push the 20 kilograms box. Hence we can say that, heavier the object, more force is required to maintain the same acceleration. Let's dive deep into what happens when we apply same force on different objects. In the first case, Ron kicks 1 kilogram of football with 100 Newton force. As we know force, F equals mass times the acceleration. By substituting the values of force and mass into the equation, we found out that the ball will accelerate at 100 meter per second square. Now let's see when Ron kicks 5 kilograms of bowling ball with same 100 Newton force. By substituting the values of 100 Newton force and 5 kilogram of mass into the force equation again, we found out that the bowling ball accelerates at 20 meters per second square. This acceleration is quite lower when he was hitting the football. So, all in all, heavier the mass, lesser is the acceleration when same force is applied. Let's take a quick recap of Newton's second law of motion, where force on an object equals mass times its acceleration. Having mass constant, the force on an object is directly proportional to object's acceleration. More the acceleration, more force is required. Having acceleration constant, the force on an object is directly proportional to object's mass. More the mass, more force is required. Having force constant, the mass of an object is inversely proportional to object's acceleration. More the mass, lesser is the acceleration. Your second law challenge: a box of mass 10 kilograms is being pulled with a force of 40 Newton across a floor. There's a friction force of 10 Newton acting against it. What is the acceleration of the box? Please write down the answer in the comments section. Next up, Newton's third law of motion, where every action has an equal and opposite reaction. See you there, and please subscribe, as it gives me more motivation to make interesting videos.